So dear students, today we will follow again the experimental setup for the photoelectric effect. Now we will see that what is there in this effect and how the experimental setup was made. Actually in the previous section we have already discussed about this. Now we discuss it in a more detail. So for that we will follow the following figure as it is drawn in the screen. The figure depicts a schematic view of arrangement used for the experimental study of photoelectric effect. This tube consists of an evacuated glass or quartz tube having a photosensitive plate C and another metal plate capital A. So here that two portions are visible, that C that is given here, that is a photosensitive plate, it is given, and another plate that is A, that is metallic plate as given. Monochromatic light from the source S of sufficiently short wavelength passes through the window W. So here the window W is also shown for the purpose that is given here. So it is passing through the window W and falls on the photosensitive plate capital C, which is also called emitter. So here the light falls on this plate C. Now the electrons are emitted by the plate C and are collected by plate A, and therefore plate A is also called collector. Now by the electric field created by the battery, so all these things happens due to the electric field produced by battery. Now the battery maintains the potential difference between the plates C and A, and that can be varied. So here we can say that whatever potential is produced here, whatever potential is produced, that can be varied and managed between C and A. The polarity of the plates C and A can be reversed by commutator. So for that the commutator is connected between these C and A with the battery or power supply, through which we can change the polarity of the tube or C and A rod. Now the polarity of the plates C and A can be reversed by commutator, and thus the plate A can be maintained at desired positive or negative potential with respect to emitter C. Now when the collector plate A is positive with respect to emitter plate C, the electrons are attracted to plate A. Now when they are attracted to plate A, obviously the flow of electron will produce. Now we know that the flow of electron is called as electric current. So here by this way the electric current is produced. The emission of electron causes flow of electric current in the circuit. The potential difference between the emitter and collector plate is measured by voltmeter V, whereas resulting photocurrent flowing in the circuit is measured by microammeter, that is indicated with yellow and red color in the screen. Now, the photoelectric current can be increased or decreased by varying the potential of collector plate A with respect to the emitter plate C. The intensity and frequency of the incident light can be varied, as can the potential difference capital V between the emitter C and the collector A. So in short, we can use this experimental arrangement of given figure to study the variation of photocurrent with respect to. Listen, here we will study the variation of photocurrent with intensity of radiation. So listen carefully. We will study the variation of photocurrent with intensity of radiation. Then we will study the variation of photocurrent with frequency of incident radiation. So this is another aspect. Now third aspect, that we will study the variation of photocurrent with the potential difference between plate A and plate C. So this is third aspect. And fourth, that we will study the variation of photocurrent with the nature of material of plate C. So in all this way, we will study the variation of photocurrent with respect to first intensity of radiation, then frequency of radiation, frequency of incident radiation, then the potential difference between the plates A and plate C, and the nature of material of plate C. Now light of different color or light of different frequencies can be used by putting appropriate colored filter or colored glass in the path of light falling on the emitter C. We can also say that the intensity of light is varied by changing the distance of light source from the emitter. So in this way, we can arrange the experimental setup and we can study and analyze the photoelectric effect through which we can analyze different points that we have discussed earlier. And now we will learn that how different part that we have discussed, that is the study of that electric current with respect to intensity of radiation, with frequency of incident radiation, with the change in potential difference between the plate A and C, and the nature of material that we used here, and we will discuss how it will affect or how to study this photoelectric effect. That is effect of potential difference on photoelectric current. This is again very interesting point and a very IMP point. Here we will discuss 2 or 3 things simultaneously. For that again we will focus on the given figure. But now in this figure, as in earlier case, we had kept PD that was fixed. Now we will not keep PD as a fixed value. Here we will keep two different things now fixed, and we will keep the potential difference variable. So here frequency of the incident light that will be fixed, and intensity I, intensity that will be fixed. Now in this case we will fix these two different quantities. So here first frequency and intensity are fixed and we will keep varying. So PD is variable. So here we say that this PD is variable. Now we will see that how it will have the effect on photocurrent. So to understand this, what we will do, we first keep the plate A at some positive accelerating potential with respect to the plate C, and illuminate the plate C with light frequency f. Here I consider the frequency to be small f, and A gradually and measure the resulting photocurrent each time. It is found that the photoelectric current increases with increase in accelerating or positive potential. At some stage, for certain positive potential of plate A, all emitted electrons are collected by the plate A and the photoelectric current becomes maximum or saturates. If we increase the accelerating potential of a plate further, the photocurrent does not increase. This maximum value of photoelectric current is called saturation current. Saturation current corresponds to the case when all photoelectrons emitted by the emitter plate C reach the collector plate A. So here it is to be remembered that there will be one condition at a given potential that will occur so that all electron emitted from plate C will be collected by plate A. And now if we increase the potential further, there will be no change in current because all the electrons are emitted by the plate C are already accepted by or collected by plate A. So now if we increase the potential, there is no change in the current, and that time the current is called the saturation current. Now we will consider the another condition. Now we apply a negative or a retarding potential to the plate capital A with respect to the plate capital C and make it increasingly negative gradually. When the polarity is reversed, the electrons are repelled and only the most energetic electrons are able to reach the collector plate capital A. The photocurrent is found to be decreased rapidly until it drops to zero at a certain sharply defined critical value of negative potential capital V0 on the plate A. For a particular frequency of incident radiation, the minimum negative or retarding potential V0 given to the plate capital A for which the photocurrent stops to becomes zero and is called the cutoff or stopping potential. So here again I am repeating, this is very important term. When we gradually make plate A to be negative with respect to plate C, please keep attention. Here we are making plate A negative with respect to C. So there will be one condition. Obviously, as A start becoming negative, whatever electrons are coming from C, they will experience repulsion. And due to that, they will not reach to the plate A. So for a certain value, there will be a particular potential at which the number of electrons reaching to plate A becomes 0. At that condition, there will be no current is observed in microemitter. And that condition, the potential is obtained. It is called stopping potential or cut-off potential. The interpretation of the observation in terms of photoelectron is straightforward. All the photoelectrons emitted from the metal do not have the same energy. The photoelectric current is zero when the stopping potential is sufficient to repel even the most energetic photoelectrons with the maximum kinetic energy that can be indicated as a K maximum, or it can be compared with the equation that is K maximum is equals to EV0. So in this condition, the electron will have the maximum kinetic energy as defined over here. Now we can now repeat this experiment with incident radiation of the same frequency but at higher intensity I2 and I3 respectively. In all these experiments, we note that the saturation currents are now found to be higher values. This shows that more electrons are being emitted per second, proportional to the intensity of incident radiation. But the stopping potential remains the same as that for the incident radiation of incident I1. Now, as shown graphically in figure as shown here, we can say that for a given frequency of incident radiation, the stopping potential is independent of intensity. In other words, the maximum kinetic energy of photoelectrons depends on the light source and the emitter plate material, but is independent of intensity of incident radiation. So this is the effect of potential on the photoelectric current. Now dear friends, we will learn the third effect of, that is effect of frequency of incident radiation on stopping potential. For that, we now study the relation between the frequency f of incident radiation and stopping potential V0. We suitably adjust some intensity of light radiation at various frequencies and study the variation of photo current with collector plate potential. The resulting variation is shown in the figure here. That is, we obtain different values of stopping potential but the same value of saturation current for incident radiation of different frequencies. The energy of emitted electrons depends on the frequency of the incident radiations. The stopping potential is more negative for higher frequencies of incident radiation. Note from the figure that the stopping potential are in order, that is V03 is greater than V02 is greater than V01 if the frequencies are in the order, that is F3 is greater than F2 is greater than F1. This implies that greater the frequency of incident light, greater is the maximum kinetic energy of photoelectrons. Consequently, we need greater retarding potential to stop them completely. Now, if we plot a graph between the frequency of incident radiation and corresponding stopping potential for different metals, we get a straight line that can be shown from the figure below. That is, now if we draw that nature, that is requirement, that is stopping potential versus frequency for different metal. Here On x-axis the frequency is given, and here stopping potential V0 is given on y-axis. If we consider different materials, then we have, suppose metal 1, we say that for some metal 1, we have stopping potential at a particular value, and it will increase gradually. For that we have some threshold frequency given at which the photoelectric effect will start. In the same manner, suppose we are taking another metal, say metal 2, then we may have another threshold frequency regarding this metal, and after that it will show the straight line. So we can say that if we plot a graph between frequency of incident radiation and the corresponding stopping potential for different metals, we get straight line as shown here in the figure 2. The graph shows that first, stopping potential V0 varies linearly with the frequency of incident radiation for given photosensitive material. Second thing, there exists a certain minimum cutoff frequency F0 for which the stopping potential is 0. These observations have two implications. First, the maximum kinetic energy of the photoelectrons varies linearly with the frequency of the incident radiation, but is independent of its intensity. Second, for a frequency f of incident radiation lower than the cutoff frequency f0, no photoelectric emission is possible even if the intensity is large. This minimum cutoff frequency f0 is called threshold frequency, and it is different for different metals. Different photosensitive materials respond differently to light. Like selenium is more sensitive than zinc or copper. The same photosensitive substances gives different response to the light of different wavelengths. For examples, UV light, that is ultraviolet light, gives rise to photoelectric effect in copper, while green or red light does not. Here we have to note that in all the above experiments, it is found that if frequency of the incident radiation exceeds the threshold frequency, the photoelectric emission starts instantaneously without any apparent time lag, even if the incident radiation is very dim. It is now known that emission starts in time of order of about 10 to the power minus 9 second or less than that. We now summarize the experimental features and observation described in this section. Here we will start. For a given photosensitive material, the frequency of incident radiation, that is above the threshold frequency, the photoelectric current is directly proportional to the intensity of incident light, that is given in this figure. Second, for a given photosensitive material and frequency of incident radiation, saturation current is found to be proportional to the intensity of incident radiation, whereas stopping potential is independent of its intensity. Here, that is explained from this figure. Now, third, for a given photosensitive material, there exists a certain minimum cutoff frequency of the incident radiation that is called threshold frequency, below which no emission of photoelectrons takes place, no matter how intense the incident light is. Above the threshold frequency, the stopping potential, or equivalently the maximum kinetic energy of the emitted photoelectrons, increases linearly with the frequency of the incident radiations, but is independent to its intensity, that is given here in the last figure. Now, the photoelectric emission is an instantaneous process without any apparent time lag, even when the incident radiation is made extremely dim. So, this is about the photoelectric effect and related experiments.